So good evening. Today we will start with FIR filter designing methods. So there are typically four methods. The first one is the Fourier series method without using window. Okay. In the second one we have Fourier series method using window technique. Then we have Fourier transform method without using window, and lastly we have Fourier transform method using window. Okay. So Fourier transform method, they are also regarded as the frequency sampling method. Okay. So, if you look over here, the frequency responses of the digital filter is given over here, and if you see, we discussed that analog low pass filter, it would be appearing, its frequency response would be appearing something like that. However, when we try to design the digital filter, so what happens, since we have seen that in the 0 to pi frequency, whatever the frequency response is there, in the pi to 2 pi region, it then becomes the mirror response of the original response. So if you see over here, for the low pass filter having a passband in the region of 0 to omega c, we have a mirror band in the mirror passband frequency band in the frequency range of 2 pi minus omega c to omega 2 pi, right? So you can just verify it from the what do you call this z plane thing. Okay, so if you see, when for designing the low pass filter, we need to place the pole near to the DC frequency. So if you see, suppose this is the region of activity of this pole. So if you see, if it is 0 and it is omega c, so we are having this one is 2 pi, and this would be 2 pi minus of omega c. Okay, so now you will be able to appreciate what is happening over here and how or why this mirroring effect it is coming in the digital frequency, okay, or in the digital domain. Now this one can also be represented in this form, wherein we are considering the frequency band in the region of minus 2 pi minus pi to pi. Okay, in the region of minus pi to pi. Okay, but for the sake of uh, ease of understanding and for the sake of doing the mathematics in an easy way, we usually deal with this frequency in the range of 0 to 2 pi, but both the methods, they are accepted. Okay, now we have this high pass filter. In the high pass filter we are having uh, this band pass or this frequency response in the analog domain, and herein we are having the high pass filter in the digital domain, and this is how the frequency response looks like. Okay, similarly for the band reject filter, it is something like this. So we are having a combination of low pass filter and a high pass filter. So again in the minus pi to pi, again you can put it in this way also, or in the 0 to pi region. Then we are having in the band pass filter also, it is something like this. So this is the digital domain frequency response. Okay. Now Fourier series method using the window, without using window. So we are having this low pass filter. Now in this low pass filter, first what we have to do, we have to draw the frequency response. Okay. Then we have to calculate the impulse response. Okay. So how will we calculating? We have to basically find out the H0, H1, H2, and Hn, and then from there we have to have this equation h of n equals to 1 by 2 pi integral of minus omega c to omega c. So herein we are basically working in the range of minus pi to pi. Okay, but in later cases we will see that we are working in the 0 to 2 pi region also. So so one of the advantages while we are designing or computing the hn values in the frequency band of minus pi to pi is that we get an integral which is quite explainable. Okay, So from here we get that hn equals to 1 by 2 pi integral of minus omega c to omega c e to the power j omega n d omega. Why this is happening? This is happening because in our last to last class we have discussed that modulus of h of omega we consider it as 1, due to which we get that modulus of y of omega, it is equal to modulus of x of omega, right? Because we do not, for a filtering, for a filter we do not want any gain, and because of that reason we want modulus of h omega to be 0, and due to this reason if you see this equation, it simplifies into this equation. Okay, so from here, because when you are designing a filter you will be knowing the cutoff frequencies. By knowing the cutoff frequencies you just put the values, and the n will be varying from 0 to n minus 1, where n is the order of the filter, and length of the filter, n is the length of the filter, and n minus 1 it is the order of the filter. Okay, so length is n plus 1, sorry, length is here, length is n plus 1. So where L is equal to n plus 1, where n is the order of the filter and 1 is n plus 1 is the uh, yeah, length of the filter. Okay, so after we have computed these things, because what happens if you see n when it varies from 0 to capital N, so we are having 0 1 2 3 up to capital N. So this capital N, it becomes the order of the filter, and the length, because of this 0 component, it becomes n plus 1. Okay, now after we have got these values, we have discussed how we can compute the transfer function of the system, right? We have already discussed how we can compute it. H of z is equal to h of 0 plus h of 1 into z to the power minus 1, and so on, right? So we will be calculating the z transform, that is the transfer function of the system, and lastly we will be going for the realization of the filter. Okay, so first we have to, what we have to do, I am again repeating the steps. First we have to draw the frequency response. After we have drawn the frequency response, we have to calculate the limits for this equation hn equals to 1 by 2 pi for a low pass filter, integral of minus omega z to omega c e to the power j omega n d omega. Okay, so we will solve this thing. So if you see, the only variable that will be remaining is the n, small n. Okay, so n will be varied in the range of 0 to capital N, that is the order of the filter. So for n equal to 0, what is the h0 value? For n equals to 1, what is the h1 value? We will compute all these hn values, and after computing those values we will be going and we will be coming to this third step, and we will be computing the hz, okay, the transfer function of the system, and then we will be going for the realization of the filter. Okay, now this is the designing process that has been discussed with you. So this equation that we discussed, what is this equation? If you remember correctly, it is nothing but it is your inverse discrete time Fourier transform. Okay, this is your inverse discrete time Fourier transform, and this is how we can compute h of n, hz, the transfer function I have already discussed with you. So let us take an example. So in this example, if you see hd e to the power j omega, it is equal to 1 in the region of modulus of omega 0 to pi by 2. Modulus of omega means, if you look into the impulse into the frequency response, so modulus of omega is, it is basically we are talking about 0 to pi. But while designing filters, we have discussed that we have to take either 0 to 2 pi or minus pi to pi, right? So here, if you see, working in the minus pi to pi region, it is convenient for us. So we will be taking the frequency response as 1 in the region of minus pi by 2 to pi by 2. Okay, because we are getting a continuous region, so we do not have to segregate it into two separate integrals. Otherwise you can also work in the region of 0 to 2 pi. Okay, but over there what will be happening, the thing is that we'll be having 0 to pi, and then you are having 2 pi, so 0 to omega c, and then you will be having another integral from 2 pi minus omega c to 2 pi, right? So you have to compute for the two integrals. Okay, so to avoid that, in this particular example we would be comfortable in working in the region of minus pi by 2 to pi by 2. Okay, so next question is that we have found out the frequency response, then we will be putting the values of the omega c and minus omega c into the integral, right? Then this is a simple integral, so 2 pi is there, so jn, because it is an integral of d omega, this jn it comes out and we get 1 by 2 pi jn. So because in this type of exponential thing, whatever is there, where for which we do not have this integral factor, so that comes as 1 by that factor, right? In this case it becomes a 1 by jn, right? Then the same value e to the power uh, theta, it comes over here, then integral is minus pi by 2 to pi by 2. So if you put it, so what we get, e to the power j pi by 2 n minus of e to the power minus j pi by 2 n. Okay, divided by, if we take this pi n outside, so we get 2j. So why I have taken this 2j, because this factor is sin theta, right? So sin pi by 2 n divided by pi n. So e to the power j theta minus e to the power minus j theta is equal to 2j sin theta. So using this formula we have converted it into this form, sin of pi by 2 n divided by pi n. Now in this case, if you see, what is the length of the filter? The length of the filter has been given. So L equals to 11. So our capital N, it is equal to 10. So small n will be varying from 0 to 10. Okay. So let's start. HDN is equal to sine of pi by 2n divided by pi n for modulus of n less than equal to 5. So why we have done this? Why we have done this? Because we have discussed that what happens, the we are dealing with type 1 filter. What is this filter? We are dealing with type 1 filter. Length is odd. If you go back to yesterday's class, order is even and length is odd, and we are having a symmetric impulse response. So we are trying to design only type 1 filter, and hence we know that order is even over here and we want a symmetric thing. So if we have values in the range of 0 to 5, then we can implement it for the, or compute it for the other n values too. Okay. So what is happening over here now? If you see, if you put small n equals to 0, if you put small n equals to 0, then this factor it becomes 0 by 0, which becomes infinite. So over there we have to apply L'Hospital's rule. Okay, limit of n tending to 0 sine of pi by 2n divided by pi by pi n. Okay, so when we have this, so there is a factor which is called limit n tends to 0 sine theta by theta, it is equal to 1. Okay, so if we want to bring this factor into the form limit n tending to 0 sin theta by theta, what we should do, we should divide the denominator and the numerator by 2. So once we do that, we get in this form, and by applying the L Hospital's rule, limit theta tending to 0, sin theta by theta equals to 1. So we get n equals to half. Another important thing over here, if you see, we have said that small n is less than equal to 5. Why it has happened? Modulus of n is given. That means there are negative values. Since we are working in the negative frequency domain itself, to start with, here also we are carefully designing this or computing this hn value, so that we are having n values, say from -5 to +5. Okay, so once you are having this, but theoretically, if you remember, we cannot have negative n values while designing causal filters. So what we will be doing after computing this, we can shift the values in the range of 0 to 5. Okay, so this is just for the sake of implementation, easy implementation. We are computing for the n modulus of n values, uh, and not for the actual 0 to capital N. Your result would be same, but this is how we need to do it. Okay, so what happens for n equals to 0? We have computed that it is half. Then for n equals to 1, we need to put in the values of n, and you will be getting this value, and hd1 is equal to hd minus of 1, then hd2 equals to hd minus of 2, and so on we have got. Now next what is happening is that now h of z, it is equal to z to the power minus of L minus 1 by 2. Okay, summation of n equals to 1 to L minus 1 by 2 h of n zn z to the minus n plus h0. Okay, so why, what this equation is doing? This equation is helping you. If you see, we are multiplying with z to the power minus 5. Okay, and here what you will be having, h0 is independent of any z value. So h0 will be having a value of this h0 multiplied by z to the power minus 5, whatever we have computed, right? On the other hand, this n at the max, it will be having a value of 5, and here the maximum value, it would be 5 minus 5 basically. Okay, so this z to the power minus 5 multiplied by z to the power 5, what you get? कैसे होगा? मल्टीप्लाई हो रहा है ना, ये -5 है, प्लस प्लस होगा ना, -10 + 0. ओके, एंड फॉर व्हाट इट इज 0? फॉर h of -5 or 5, right? So what it is happening? So for 0 we are having half over here, then h of 1 we are having 0.32, again over here it is 0.32. Okay, then 2 is 0, then we are having minus 0.11. Here also you will be having minus 0.11. Then again you will be having 0, 0. Then 5 is 0.06. Here also you will be getting 0.06. Now this factor, this 5 factor, what it will be having? It is getting to 0, right? Now if this is 4, minus 5 plus 4, what you will be getting? -1. -1 मतलब ये -4 वाला, it will go to the 1. So it is shifting towards the right. So this whole value, it will now be given by, it will be in the order of h of minus 5, h of minus 4, h of minus 3, and so on. However, while you would be, because these are the values, numerical values, and while you are multiplying it with this one, what you are getting, this will be become the modified n, it will be 0, 1, 2. So you will be getting h of minus 5 into z to the power minus 5, sorry, z to the power 0, plus h of minus 4 into z to the power minus 1. Okay, so then h of minus 3 into z to the power 2, and so on. You will be getting in this way, right? So at z to the power 5, what you will be getting here, the 5 you will be getting as the half into z to the power minus 5, l minus 1 divided by 2. Okay, so in this way, if you see, we are getting this thing. So 0.5 z to the power minus 5 plus 0.32 z to the power minus 4 plus z to the power minus 6 minus 0.11 z to the power minus 2 plus z to the power minus 8, and so on. Okay, so in this way we will be getting the values, right? Any doubt? So this is in the form of linear phase structure implementation method. Okay. Similarly, if you consider this high pass filter, the same method will, we can have two yeah, integrals. The rest of the method, it remains the same. We get hdn equals to 1 by pi n sine of pi n minus sine of pi by 4 n for n modulus of n less than 5. So from here n is 10. So L minus 1 by 2, it is equal to 5. So modulus of n is. Okay. So then we compute the value, and by the same method we get this equation itself. Similarly, if you want to design the band pass filter, so in the band pass filter, if you see, you are having this frequency response. So you are getting, so see, pi by 4 to 3 pi by 4. So pi by 4 to 3 pi by 4. So you compute the value, and then you compute the HN values, and over here you calculate the XN. Okay. Then coming to the phase response values, we already discussed how we can find out the phase response value. So what you need to do is that, say for example, I have taken the last example over here. What we have done, 0.5 z to the power minus 5 minus 0.32 z to the power minus 3 plus z to the power minus 7. Okay. So what we have discussed, we will be replacing z with j omega. Okay, minus of j, yeah, j omega. So this is 0.5 it is z के जगह पे e to the power j omega minus 5 is already there, minus 5 j omega minus 0.32 e to the power minus j3 omega plus e to the power minus j7 omega. Then you have to get this, and then we know this equation, e to the power omega j is equal to cos omega plus sin j omega, right? Then we just have to put in the values and solve it, and what we will be getting, we will be getting in the form of a plus jb, and after that you have to compute the a and b, and from the a and b at the 5 locations you compute the modulus and the phases. Okay. So next thing is that design a low pass filter with the following specification: cutoff frequency 500 Hz, sampling frequency 2000 Hz, order of the filter capital N equals to 10, length of the filter L equals to N plus 1 equals to 11. So over here, if you see, we are not given with the frequency responses or the values where it should be passing through in that way in the form of pi, right? In the form of radians. Here we are given with hertz. So what we have to do, we have to normalize the cutoff frequency. This is the first step. So what we have to do, we have to compute the normalized cutoff frequency omega c equals to 2 pi fc by fs. Fc is 500 hertz and sampling frequency is 2000. From there we get pi by 2. And then from here we want to find out the HD omega, which is equal to 102 modulus of omega pi by 2. So this is the first example that we saw. So if you get this kind of numerical, then you have to first compute the normalization of the cutoff frequency and then you go forward. Okay. So step by step procedures it has been given, whatever I have just told you. So in the next class we'll be dealing with this window functions. So first try to grasp this thing and try to solve it. Maybe we'll take 2 days to get hold of this low pass filter, and then we can go towards the window function. So please do it. If you face any trouble, just let me know.